Good morning. I want to show an example of how to do an energy pie chart. So let's read our scenario first. Ball is held above the ground and then is dropped so it falls straight down. Assume that the ball has not struck the ground yet in your last snapshot. So if you don't remember anything about energy pie charts, um, we use those to show all of the different forms of energy for one snapshot of time for an entire system. So remember, a system is just all the objects that you're thinking about, that you're considering for your problem or your scenario. And then we have the different symbols. In my example here, I have the popper is like starting to launch itself, which is what the little GIF is. Since it's starting, it hasn't used up all of that elastic energy, which is why I have a section of the pie graph being US, but it is starting to move, so I've given it kinetic energy. And then because I want to account for air resistance, I'm going to put thermal energy. Um, but the key with snapshots is they're across time, right? So for snapshot one here, need a pen. For snapshot one, my object is not moving, so there's not going to be any kinetic energy, but it does have height, so that means I'm going to have gravitational energy. So I'm going to put UG here. But I'm not going to put any other forms of energy. You might be thinking, but aren't we going to account for air resistance? And we are, but you cannot have thermal energy in your first snapshot because thermal energy is the energy that is no longer usable for us. So that's going to be, that would be like you wake up in the morning and your energy bar is not full. It's at like you already are starting halfway, which doesn't make any sense. You wake up and that's the total amount of energy that you have. So this is 100% of your starting energy. You can't start at 50. You have what you have, and that's what you have. That's what you start with. So we won't be having thermal energy for air resistance in that first snapshot, but we can in our second. So it started to move, but it still has height, and I do want to count for thermal because it seems to not be like very far into its path. I'm going to say that most of its energy is going to be in gravitational potential energy. So I'm just gonna guess, give myself like roughly 2/3, and I'll label it UG. And then the rest of it, I'm going to divide between the kinetic energy because the object is moving and the thermal energy because of the air resistance. Great. I don't really know if these percentages are appropriate, but it doesn't really matter because we're just looking for those changes over time. So now let's move on to snapshot 3. Now my object is just about to hit the ground, like it is this close from the ground. Because it is so close to the ground, we can assume that that gravitational potential energy stored in the height is negligible. We can ignore it. So I'm not going to be writing UG, but it is moving really fast. So I'm going to give myself lots of kinetic energy because it's moving as fast as it as ever would. And now I'm going to give myself the rest to be thermal energy, and notice that the thermal energy has grown from the previous snapshot. That would make sense. The further you are along in your path, the more thermal energy, the more energy that you have that isn't usable anymore because of heat. Okay, so therm. Okay, and that would just be an example. Okay, hopefully this has been helpful.